when a reaction occurs, we can tabulate how, for different reactions, when you have, a mole of a reaction, we can tabulate exactly what the heat loss is. And what we do is we keep track of it at a certain standard state under certain conditions. The change in enthalpy will be different at different temperatures or different pressures. So we assume that we're at 25 degrees C and 1 bar pressure. All substances are in the most stable form, 25 degrees C, and all solutions are at 1 molar. And then you write out the standard state. You write a little degree sign there, delta, the change in enthalpy standard state. The standard state of reaction, it turns out it doesn't depend on T and P because it happens at a given temperature and pressure. And then so for each of these different equations, you can measure and write out what your heat of the standard heat of reaction will be for that system. We say heat of reaction rather than enthalpy because it is the heat transferred at constant pressure. Note that these two will be slightly different because we're using they actually have water in a different state. And we'll learn how to take into account changes due to the fact that there's phase changes as well. There's enthalpy associated with phase changes, and we'll revisit that when we look at phase changes a bit more. So these reactions would actually have two different enthalpies of reaction because their components are in different phases. Okay, so if we have these tabulated heats of reaction, we can relate that to what's going on in the system. Yeah, so once we have the delta H at one set of conditions, we can calculate the delta H, the change in enthalpy at different conditions of interest, which we'll revisit next week and then later in the semester as well. All right, so let's take a look at this. So we've tabulated this heat of reaction for burning of propane. So how much heat can be produced by burning 9 kilograms of propane at 1 atmosphere pressure? That's pretty much what you get in a standard canister of propane that you pick up at the store for grilling. So let's see. So the heat transferred at constant pressure is going to be is equal to the reaction enthalpy. And if we're not careful, we won't get exactly this heat. But assuming that we do everything, we get all of the heat out that we could, then the maximum heat we can get out at constant pressure, because the burning is occurring at constant pressure, even though the gas is pressurized. We would need to. So this is the standard state heat of reaction at 25 degrees C. So we're going to estimate that we actually are grilling at 25 degrees C. That's a good temperature to grill at, I suppose. And for 1 mole of propane, so it's for the reaction as written, for 1 mole of propane, then this is the heat you get. So we have more than 1 mole of propane. So the molar mass of propane is 44.1 grams per mole. And so 9 kilograms, 1,000 grams per 1 kilogram. That and then we have minus 2044 kilojoules per 1 mole of propane burning, sorry, let me add this in. Let's get all our things right. It doesn't matter what order we do the conversions in, but just to make things simpler here. Grams for 1 mole. There we go. And now for 1 mole of propane burning, we have minus 244 kilojoules. So the moles cancel, the grams cancel. And what we get out is 4.17 times 10 to the 8th joules. So that's a lot of energy. You can imagine, that's that propane can burn for 2 or 3 hours. So we're getting a lot of energy off from burning that propane. Okay, and so I like to be precise here. That's a minus there. That's the heat given off by the reaction. The heat gained by the environment would be the positive, because Q of system, which is the propane, is equal to minus Q of surroundings. So it's giving off heat. It heats up the surroundings. Okay.